Hello students, welcome to this lesson. This is the last part of chapter 5, continuity and differentiability. This topic is known as Rolle's theorem and mean value theorem. So this lesson I have divided into two parts, lesson 1 and lesson 2. Rolle's theorem, first part, then the mean value theorem. So these are the two concepts we are studying in this chapter. In fact, in some of the other textbook, it is coming under application of derivatives, but in NCERT textbook they have included under continuous Rolle's theorem. See, let f from a to b, that is closed interval, to r, real number, be continuous on ab, that is closed interval, and differentiable on open interval ab such that f of a equal to f of b. This is the first condition. Of course, first one is it should be continuous. Second one is it must be differentiable. There is the second one. F of a must be equal to f of b. That means the value of the function at the end point a and b, they must be same, and a and b are some real numbers. Then if these three conditions are satisfied, underline, first one is continuous on closed interval, second one is differentiable on open interval, and third one is f of a must be equal to f of b. That means value of the function at the end point a and end point b both must be same. If these three conditions are satisfied, that is what the Rolle's theorem says. For some, of course, a and b are real numbers, then there exists some c in the interval, open interval ab, such that f dash c equal to 0. So this is the theorem. Let us try to understand the meaning of this theorem with the help of a diagram. Let us say there is a function y equal to f of x. This is f of x, and a, this is the starting point a, and this is the end point b. So ab is the closed interval where it is continuous, and this is f of a, and this is f of b. So the value, the perpendicular line which I have shown there, that is f of a and f of b. Now let us say at the point, one particular point c, you can draw a tangent parallel to the x-axis, because the function is continuous. See, this is the thing you have to understand. Function is continuous, f of x is continuous, and f of a and f of b both are equal, means unless it is not constant, it has to go up and then come down. This is one possibility, or the other way also possible. It can come down and then go up. Whatever may be the case, in the case which I have shown here, it is first going up, that means increasing, then coming down, decreasing. So at some point it should be the maximum point. Of course, we are studying maximum minimum in this chapter, in the next chapter. So there at that point c, we can draw a tangent, and that tangent is parallel to x-axis. But we know that slope of the tangent is nothing but it is f dash x at that particular point. So c is the point, therefore f dash c equal to 0. This is the geometrical interpretation of this theorem. That means whenever the function is such that the curve is continuous with two conditions, f of a and f of b both must be same, then in between there is one point c where f dash c is 0. That is, the derivative of the function is 0. This is what the Rolle's theorem says. So proof is not there for this theorem in the syllabus. Let us observe some of the important things. Consider a function y equal to f of x such that f of a equal to f of b equal to 0. So that means it is cutting x-axis at 2 points. Say this is the situation. So the function y equal to f of x cuts x-axis at a and x-axis at b, so that f of a and f of b both are 0. Then see here we can draw a tangent parallel to the x-axis at the maximum point, a maximum point. So that point, let us say c, there f dash c is 0. So this is the meaning. This implies we can interpret like this: between two zeros of f of x, two zeros, because f of a is also 0, f of b is also 0. These are the two zeros of the function. There exists a 0 of f dash x, the derivative of the function. So this is one interpretation. Similarly, actually the Rolle's theorem says at least one such c must be there. See, here is a situation. A is one point, B is another, of course, that is lower limit and upper limit, that is a starting point of the function A domain, and B is the endpoint, closed interval. So now y equal to f of x. See, here is one tangent we can draw. This is f dash c equal to 0. We can also draw one more tangent here. Here also f dash d is 0. That means between two zeros here, there are two zeros actually. So f dash c is 0, f dash d also 0, c and d. That means there are 2 points where the derivative is 0. So the theorem says at least one number, that is c, must be there. So between two zeros of fx, there exist two zeros. So there may be more also, but at least one zero will be there. So this is the meaning of Rolle's theorem. Now let us try to solve a few problems on Rolle's theorem. First one, f is from 2 to 5, that is closed interval to R, defined by f of x equal to x square minus 7x plus 12. This is a quadratic polynomial. Now f is, see, this is the example for Rolle's theorem actually. F is continuous on closed interval to 5, because every polynomial function is continuous. We have studied under the continuity, therefore this is a continuous function. So the first condition of the Rolle's theorem is satisfied. Second, f is also differentiable on the open interval to 5. So that is the second one. And the third one, f of 2, this is, you substitute here, this is 2 square 4, 7, minus 7 into 2 is minus 14 plus 12. When you simplify, you get 2. Then f of 5, when you substitute 5 square minus 7 into 5 plus 12, simplify, it is 25 minus 35 plus 12. You can see this is also 2. Therefore now three conditions of the Rolle's theorem are satisfied. First one, it is continuous in the closed interval. Second one, it is differentiable in the open interval. Third one, f of 2 and f of 5, that is the value of the function at the end points, both are equal because both are 2. Therefore f of 2 equal to f of 5. So all the three conditions of the Rolle's theorem satisfied. Therefore what should happen? So now let us find f dash x. This is 2x minus 7 differentiating x square minus 7x plus 12. This implies f dash c will be 2c minus 7. Now what should happen? Where this c should lie? It should lie between 2 and 3. Let us check. Now f dash c equal to 0 gives 2c minus 7 equal to 0. This gives c equal to 7 by 2. Now check what is 7 by 2. 7 by 2 is 3.5, and 3.5 lies between 2 and 5. Therefore now 7 by 2 lies in the interval 2 to 5. This is what the Rolle's theorem says. So this is a very good example to show the truth of Rolle's theorem. But here you have to remember one thing. Rolle's theorem is valid only when the first three conditions are satisfied. First one, continuity. Second one is differentiability. Third one is at the end point they must be equal. If these three conditions are satisfied, then when you take f dash x, so there exists a c such that f dash c will be 0, number one, and that c lies in the interval, given interval, that is open interval. So this is the essence of Rolle's theorem. Now verify Rolle's theorem for the function f of x equal to x square plus 2, a equal to minus 2, and b equal to 2. So what is the first condition? So first let us write f of x equal to x square plus 2. Given interval is a is minus 2, b is 2. So the function f of x is definitely continuous in the closed interval minus 2 to plus 2, because polynomial function is continuous. Second one, this you have to write. The function f of x is differentiable in the open interval minus 2 to 2. So this is the second condition. Now let us check the third condition, f of minus 2. This is minus 2 square plus 2, 6. F of 2. This is 2 square plus 2. This is also 6. So the end points are equal values, value of the function. So f of minus 2 equal to f of 2. All the three conditions are satisfied. Now as per the Rolle's theorem, what you have to do is now find f dash x. So f dash x is 2x. Therefore f dash c will be 2c. Now what is the condition? F dash c equal to 0 implies 2c equal to 0. This implies c equal to 0. Now we have to check this one. Where is this c now? It is in the interval minus 2 to plus 2. You can check. Now c equal to 0 belongs to minus 2 to 2. So this verifies the Rolle's theorem. Now verification of the Rolle's theorem statement. See, these are the things you have to understand. Rolle's theorem says this one. Let f be a function from closed interval a b to R continuous on the closed interval a b and differentiable in the open interval a b such that f of a equal to f of b, where a and b are some real numbers. Then what the Rolle's theorem says is there exists some c. It is not specifying only one c. It may be more than one also, but at least one c must be there in such a way that in a b such that f dash c equal to 0. This is the statement of the Rolle's theorem. Now what are the steps? Because sometimes question will be verify Rolle's theorem for a given set of questions. These are the steps you have to remember. Step 1 is show that f is continuous on AB whenever you want to verify. Second, step 2, show that the function is differentiable in open interval AB. Then step 3, show that f of a equal to f of b. These are the three necessary conditions. So then step 4, show that there exists c belonging to AB such that f dash c equal to 0. So this is the essence of Rolle's theorem. Now let us go to the exercise. There are a few questions in exercise. Here there are two types actually. One is verifying the Rolle's theorem. Sometimes show that Rolle's theorem cannot be applied here. Rolle's theorem is not applicable in the following example. That is also possible. So these are the two categories. Exercise 5.8, first question. Verify Rolle's theorem for the function f of x equal to x square plus 2x minus 8, x belonging to closed interval minus 4 to 2. So what is the method? Let us write f of x equal to given function x square plus 2x minus 8, then a is minus 4, b is 2. Now the function f of x is continuous in the interval minus 4 to 2. We know that it is a polynomial function and every polynomial function is continuous. Therefore you have to write it, that's all. Second one, the function f of x is also differentiable in the open interval minus 4 to 2. So these are the two things. So the first two conditions are satisfied. What is the next one? We have to find f of minus 2. F of minus 4, sorry. Minus 4 square, 2 into minus 4 minus 8. So this is 0. Similarly, f of 2. So this is also 0. You can check it. Therefore, f of minus 2 equal to, so f of minus 4 equal to f of 2. So the end points, the function values are same. So the first three conditions necessary for Rolle's theorem is satisfied. Continuity, differentiability, end point. Now what you have to do? F dash x you have to find. So f dash x is 2x plus 2. Therefore f dash c will be equal to 2c plus 2. But this is 0. F dash c equal to 0. This implies 2c plus 2 equal to 0. This implies c equal to minus 1. Now where is this minus 1? Minus 1 belongs to the interval minus 4 to 2. Now minus 1 belongs to minus 4 to 2. So this satisfies, or this is the verification of Rolle's theorem. That means all the conditions are satisfied and it satisfies the statement also. Next example, example 2. Examine whether Rolle's theorem is applicable for the following functions. First one, f of x equal to greatest integer function x for x belonging to the closed interval 5 to 9. Let us check. See, first one is f of x equal to greatest integer of x for x belonging to 5 to 9. F of x equal to greatest integer function is not continuous at all integral values. This we have proved in the continuity. Therefore, f is not continuous at 5, 6, 7, 8 and 9. So, therefore, Rolle's theorem cannot be applicable here, because the first condition itself is it is applicable only for continuous functions. This is not a continuous function, so we cannot apply Rolle's theorem here. So, this is the example. Next. See, example 2 has 3 parts actually. Examine whether the Rolle's theorem is applicable for the following function. Function given is f of x equal to greatest integer function x for x belonging to minus 2 to 2. Now, f of x equal to greatest integer function x belonging to minus 2 to 2. So, once again, is not continuous at all integral values. So, f is not continuous at minus 2, then minus 1, 0, 1, 2. So, definitely Rolle's theorem is not applicable. So, first one and second one almost same. So, this is the second part. Third part, examine whether the Rolle's theorem is applicable for the following function. This is third one. F of x equal to x square minus 1 for x belonging to 1 to open closed interval 1 to. So, first one. See, f of x is x square minus 1. This is a polynomial function. And definitely it is continuous. So, the first condition is satisfied. It is also differentiable. F of x equal to x square minus 1 for x belonging to 1 to 2 is differentiable on open interval 1 to 2 also. So, the second condition is satisfied. Let us check the third condition. What about f of 1? 1 square minus 1, 0. What about f of 2? 2 square minus 1, 3. But f of 1 is not equal to f of 2. Therefore, the third condition is violated. Therefore, you cannot apply Rolle's theorem here. So, we have to write, therefore, Rolle's theorem is not applicable. So, this is the third part of the second example. Thank you for watching this lesson, very small lesson. I have divided this into 2 parts, Rolle's theorem separately and mean value theorem. Please watch the lesson and subscribe and share with your friends. Hope you are watching all the lessons of differentiation, that is continuity and differentiability. This is the last concept, as I told you. Let me complete this chapter with one more small video lesson on mean value theorem. With this, actually, the chapter 5 is completed. Let me tell you one thing. In the beginning, I started video lessons, recording my video. Then I actually shifted to this PPT presentation because some students suggested this is better because this is more appealing. Though it takes more time for me to prepare, I am now changing my style of presentation using PPT. Another reason is I can cover more topic and more examples with this mode. Hope you will appreciate, and please subscribe and share. Let us meet in the next lesson with the mean value theorem, and as I told you, that will be the last lesson on chapter 5. Thank you. Let us meet again.